having a kind of a robot cloud brain is fantastic, but there's also a physical dimension to human-robot interaction. And when we engineer robots for physical contact with humans, we have to be really careful about our selection of materials. I mean, I think we would all agree that, we want to have materials that are safe, that, with contact they're comfortable, that they preserve natural mechanics, they adhere to these principles of biomechanical compatibility. What's disruptive, though, is that we know fundamentally that it's actually impossible to engineer rigid materials to match the elastic and rheological properties of our natural biological tissue. I mean, if you really think about it, I mean, you can only go so far with miniaturization, with flex circuit technologies, even these kind of emerging so-called deterministic architectures for stretchable electronics. So it was kind of my perspective and my kind of disruptive type viewpoint here is that for human-robot interaction, we actually have to get rid of rigid materials, okay? Get rid of the metals, get rid of the hard plastics, even the crystalline semiconductor-type materials, and shift over to the soft side of the spectrum, elastomers, fluids, colloids, gels. So this introduces, I mean, a lot of challenges and it's somewhat unsettling, especially for industries that have historically focused on rigid solid state. And I'm not saying that this is necessarily appropriate for existing engineering applications, but when it comes to wearable computing, medical robotics, pretty much anything wearable, implantable, ingestible, anything in robotics that involves physical human-machine interaction, we really have to carefully re-examine the role of rigid materials and look to this other end of the spectrum in areas like soft microfluidics and what I'm terming kind of more generally soft matter engineering.
Okay.
Thanks. I'll challenge the dialogue a little further. Great futurist Arthur C. Clarke once said, "How inappropriate to call this planet Earth when it is so clearly ocean." He was onto something. The ocean really is different from the world we and our technology know. Undersea, there's no air, no internal combustion. Radio signals travel roughly one wavelength. That's about 12 centimeters for Wi-Fi. It's not much of a hotspot, is it? Temperatures in the ocean are a challenge, right? The ocean is bitter cold. Pressures crush, salt corrodes. This is such a different environment that it hid from our science an entirely new form of life dependent on chemistry, not on the sun, until 1977. Also hid plate tectonics, by the way. We didn't know that either, kind of relevant here in San Francisco, right? So what does that mean for marine robotics or disruption? In the ocean, we use the water to our advantage. We can use buoyancy engines like the undersea glider you see here. Simple alkaline batteries, buoyancy we can run for days, months, years. We can go fast too, though. Supercavitation techniques are coming to commercial maturity. That's going to allow robots that'll be able to perform like dolphins. So our ocean robots, fast or slow, have a weakness: very limited telemetry. 1200 baud. This is not streaming video. So what does that mean? It means they need to be very, very smart. You need to trust the machine to listen to something like a text message command and carry out its mission properly. Come back home, go do its task, whatever. The mission is driven by the smart robot. So why am I excited? It's such a hard, challenging environment. What's so exciting? Well, first, there's the opportunity. The ocean regulates the climate. It feeds our citizens. It holds vast stores of energy. And it transports most of our commerce. Huge opportunity for economic growth. And then there's the fact that the challenge forces us to seek disruption. We're doing pretty well mechanically, but we are just now beginning to network our ocean. Not sure if we're going to get the internet of sock puppets from the 90s, or if we're going to get an internet of social media and tweets. But if we get tweets, I'm not sure what to call a tweet from an underwater robot, but I'm pretty sure it's disruptive. So I think it's the future, and all apps, bots, and business models are welcome. The water's fine.
So I'm going to talk a bit about human-robot interaction. So what we can see over the next 30 years, we're projecting to see a decrease in the growth rates of working-age population. And what that means for the individual workers, they're going to have to be much more productive. So we can think of a person managing maybe teams of robots to help them out, and not just physical labor, but intellectual labor. The issue, though, is that we're going to need these robots to be smarter, adaptable, and quicker learners. And machine learning with big data is not going to be enough. And let me explain why. The first thing is that the kind of tasks you're going to want to teach these robots are very specialized and customized, idiosyncratic, very personalized. You're not going to find the training data available for that, and you're not going to want to provide the training data for that by doing something 1,000 times. You need to get them to learn much faster. We're going to have to learn behaviors, so the stimuli, the decision-making, and the actions, not just categories, which machine learning is often good for. And then how do you represent the tasks? You're going to have to think about how, when we do things, we iterate, we loop, we have special cases, we have subtasks. We have to teach them how to learn algorithms. And just a single feature data point is not going to be able to be good enough to capture that. So how do we do this? There's a couple things I can propose. The first one is, let's do what we do best, natural human social communication. Most people are not going to be computer scientists. They're not going to be able to program the robots using consoles or even GUIs. So let's do the natural things we do when we collaborate with robots. How I use my gesture to point out what's important to a task, how I increase the emphasis of certain words to show what's relevant or salient for that. The other thing is on the algorithmic side, we want to think about active learning, not just passive observation, but actually allowing us to learn faster with fewer examples. We want to be able to teach the robot concepts, high-level concepts like goals and constraints, so that they can generalize and adapt if things change. And more importantly, we want to have interaction in the learning, just the way we learn ourselves. The robot should be able to ask questions to clarify ambiguities and to speed up the learning process instead of being bombarded with thousands of examples. And us as humans, we want to be able to correct and interrupt the robot and correct it on the fly so that we won't get frustrated with those robots. And that's basically social guided task learning. Thank you.
Hi. So by the time I started my PhD at Stanford, and in the last 10 years I have been at Cornell and Stanford as a professor, the question of whether devices and robots should be connected does not even arise. I always ended up doing research and products with connected devices and robots. The real question actually became was that how can we take this stream of data from all the connected devices and all the connected robots and convert it into knowledge? A knowledge which could be used by crawling the internet, like there's a lot of YouTube videos, WikiHow recipes. Every robot interaction in the world gives us a signal and tells us something about how things should be done. For example, the Roomba example that the panel chair gave today. So the goal of this RoboBrain project that we started at Stanford, Cornell, Berkeley, and Brown is to really make a big knowledge engine that the robots can query for performing many tasks. They could range from household tasks, automated car, or industry robots. The same idea we have been applying in a company called Brain of T that I have founded, where we use machine learning and a lot of data analytics to convert data from robots and sensors into meaningful knowledge. Some examples include like a thermostat, which is $80, is already connected. What can make it a $250 thermostat? It is converting data into knowledge that you can control. Same thing goes for robots. What makes a Roomba robot more interesting? If it has the knowledge to vacuum your things more carefully. Today, I'm just going to show you this video where a person comes in and he says in natural language.
Finally, add raspberry syrup to the mixture.
So the robot has no knowledge of what the recipe affogato is. All it sees is a new context, a new environment in which there are these different objects. There are these different things like coffee and so on. So it is querying the RoboBrain on figuring it out on how should it do, what does it mean to have a coffee in a cup. And there is no coffee, but it's in a coffee dispenser. There's no cup, but it's used a bowl. So it knows by querying the brain how to do things, how to make use of the context to make relevant inferences and control actions and convert that into things. So the goal of this RoboBrain project, which is actually already available, and any robot can now use this SDK to connect to a brain, get the information out, and every device can connect to my company, Brain of T's SDK, to make it smart.